first.
Thank you.
This is weird, y'all. So I'm on my Bluetooth headset. I called in and it's saying my speaker's not working properly, which I know it's not. So I might have to continue without audio. So what I'll do is you may just be watching my mouse move around the screen, okay? Was that a woohoo, Jody?
You called in with your phone, you said?
Yeah, I have to call in with my phone because, well, these things, because my audio card on my computer apparently is shot.
I see. I'm like, we can hear you.
No, yeah, you can hear me fine. It says it may not include audio, so just a heads up. Did y'all? Hey, by the way, have y'all watched the video from last week?
No, we're sorry.
No, nobody.
The video that we had our class.
Yeah.
Oh yeah, no.
Number one.
No, I felt like I didn't need to go back and review that. I was listening.
Okay. Well, yeah. It may not have audio either.
It did have audio actually. I listened to it today and it had audio.
Good. Okay, good. So maybe, cross your fingers, it will have audio today, okay? If not, I think the recording creates like an audio file and a video file. I'll get both of them to y'all somehow, okay? If I can. Cool. Good deal. All right, so there we go. We're recording. All right, so welcome to week 2, everybody. First things first, though, let's talk about project presentations. I tasked you last week to think about how you want to do a project presentation for this class, 2 of them. 2 options. One is everyone for themselves, technically. You can help each other out along the way, do your little Eric's not invited group situation, or invite me, it's fine. But you know, work on your own data analysis, work on your own way of presenting, work on your own PowerPoint. Or I can pair you up randomly to a group, two different times, which means you're going to get paired up with each other automatically, right? So all that to say, did we come to a conclusion?
We didn't really chat about it. I mean, I'm fine with group. I find that I learned something from kind of the collaboration. If I don't, or if I'm going off the wrong way, usually one of the two can bring us back. Or I like group. I'm fine with group.
I like group.
Okay, that's 2 for group. Manta and Kara.
Same here. Whatever works for everyone.
Okay,
I was just going to say, why don't we do one solo and one group?
It doesn't work like that.
Too.
Oh, okay, then all group. I'm from the Midwest, so whatever.
I don't know what that means, but whatever.
I'm generally agreeable. It's just how it happens.
Okay. The reason I want it to be all or none is because I either want everyone to work with each other or everyone to work individually and still have the opportunity to, of course, bounce ideas off each other. But the 2 groups means that Kara and Chris and Jody and Manta, right? And then Manta and Kara and then Chris and Jody, right? I want it to be equally distributed so everyone works with everyone, right? If groups were the way to go. Yeah, you see what I mean?
Mm-hmm.
Okay. What are we snacking on?
Sorry, I meant to put it on mute.
No, I'm asking. No, what do I'm just asking. Okay, I've got my PB&J ready to go, so.
Well, I'm jealous.
Not now, but later. Okay, so Jody, also another call out for you. What do you see in that top right-hand corner?
Of the slide, it says project present. 3 bars.
Oh God.
That was your idea, Jody.
No, it wasn't. It's in the book, right? And it's not true because he.
Oh yeah, it is in the book. But I thought you said it'd be nice to know.
Maybe I did, but I don't remember. I just remembered the lines in the book did not match what I felt was the degree of difficulty. Bars,
So,
not the
so
lines.
Tara and Monta, just so you know, this is where it came from. Was that person in the yellow or whatever color
I
that is? I can't
remember
tell. Stripes.
suggesting this.
Yeah. So the worlds are colliding. Like I told you before, it's going to happen. So Jody, I brought it back. I actually brought it into EAM 630 last semester, so they benefited from it as well. Several people said they liked it. It kind of gave them like a, hey, whoa, open your, like, make sure to pay attention kind of situation. So in this slide, you could all take a nap, right? Okay. So Jody, what did you say you wanted to talk about?
How did you know that?
I was gonna say that's awesome.
Were you in our chat? Are you like somehow spying on us? Because we had a long chat about this where I asked if anybody minded if we discussed it.
No. This is what I wanted to do tonight. Remember, I told you I wanted to review some things, some key things from EAM 630 to make sure we're all on the same page. Because for some of you, it's been a couple of weeks. For some of you, it's been quite a while, a couple of months, almost half a year. So let's talk about what a p-value is. The p-value itself is the probability of something occurring or rather not occurring, depending on what you're looking at, right? So when we run statistical tests, whether they are chi-square, whether they are logistic regression, linear regression, correlation, generally there is a generated p-value, right? And that is, there's a lot of math behind it. I don't want you to worry about, because you don't need to worry about it. That's not, this is not a statistics class. I think I may have said that last year, but this is a data analysis class. So I want you to understand the concepts and really recognize kind of what they're telling you. I'm never going to ask you to calculate a p-value by hand, okay? Okay. So going back to the P itself, it stands for probability. And what we mean by that is a p-value of less than 0.05, which is kind of the industry standard, is basically what that means is that there's a 5% or less chance, less than 5% chance rather, that something happened just by chance, right? So if we're talking about retention of students in this program, right? And we found that students who study 10 hours a week were more likely to, like 5 times more likely to stay in the program throughout the entire time. And that was a statistically significant finding at the P is less than 0.05 value. That means that there's basically a less than 5% chance that we would come up with that same conclusion just randomly, okay? Using let's just say we sampled all the students that Agnes got, and we sampled them 100 times. Out of the 100 times, we would expect less than 5 times for our data to not match, right? For our analysis to not show the same thing. Because there is such a strong relationship between variables that p-value is so low, essentially saying that, you know, if it happens to not be true, which we're going to talk about what that means, if we happen to make a mistake and we find error in our analysis, then we know that it's really a slim chance that would occur. It's basically giving us a recognition that our analysis is meaningful, right? The results of our analysis are meaningful. There is a less than 5% chance that this just happened at random, and that the way we're analyzing these data, if we find that there is a difference between these groups, it's not just, you know, hunky-dory, right? That's a technical term. But rather, there is enough differences in the data that we don't think that it could happen randomly, okay? So I can continue to elaborate on p-values all night long. I can give you a million types of examples, but essentially what we're saying is a p-value of less than 0.05 means that there's a less than 5% chance that the outcome of that statistical test happened randomly, okay? And basically what that means is you should trust the results. Maybe. Trust the results. okay? So remember, this is all building into this idea of null hypothesis statistical test or statistical testing, right? So what we're doing is we're measuring these probabilities that there is an effect, right? That there is a difference between two groups or three groups, or that there is a strong predictability of your high school GPA based on your, I don't know, math scores in ninth grade, right? We're basically making predictions, we're stating hypotheses. The way null hypothesis statistical testing is grounded is we don't measure whether or not we determine the hypothesis to be true, but rather we always try to find data that supports our rejection of a null hypothesis. Because in all honesty, we have so much error floating around, so much, other stuff happening, that it's really hard to prove a hypothesis is true, right? But rather we can say, look, our data support a rejection of the null hypothesis, that there is an effect, that there is a relationship based on our data. And so that is exactly what we're trying to do here, is use our p-values, look at our analysis, whatever we're running, t-tests, linear regressions, logistic regressions, look at those analyses and basically say, we can reject the null hypothesis based on, a chi-square value of 15 and an associated p-value of less than 0.05. That means that there is a difference between, or there is an association between these variables, or no association between these variables, etc. As we talk about different statistical tests, you're going to hear me say a lot of things. And it's one of those, maybe y'all might want to start like a shared Google document where Eric says, logistic regression, he's probably going to talk about likelihoods, right? Or Eric says t-test, and he's going to talk about comparing two means, right? Or two averages or two groups, right? Eric's talking about linear regression, which means we have categorical and continuous predictors of a continuous outcome, right? So I know I'm giving you a lot of examples, and maybe I should just stick with one, but I'm trying to impress upon you that we're doing this for any parametric test. What does parametric mean?
This is the one where I'm thinking about the assumptions. This is where my brain is going, right? We can assume that something follows the normal like pattern of data.
Distribution.
Yep. Normal distribution of error.
Yep.
Normal distribution of error. What about, are you ready? I'll give you the first letter.
That's the linear, right?
Yes, linearity, right?
Mm-hmm.
Oh
right?
Yeah. Homoscedasticity.
Homoscedasticity.
Everybody, look, we do this every semester. Are you ready? We all say it at one time. Ready? 1, 2, 3.
Homoscedasticity.
Oh, terrible. So yeah, all of those are assumptions that we make based on these parametric statistical tests. Non-parametric tests don't meet those assumptions, right? And they're usually based on smaller sample sizes that are not generalizable to the broader population, okay? So when we talk about parametric analyses, parametric testing, we're talking about these sorts of understandings of related p-values, hypotheses, null hypotheses rather, all the different types of testing methods, and generally whether or not there's a difference, whether or not there's an effect, whether or not the likelihood is statistically significant, whether or not the groups are different, right? All those sorts of things. It's going to be one of these things where you're going to get it eventually. And in fact, you're going to get it during this class because we're going to talk about it so much. But it is something to think about. Remember how I gave you all that flow chart at the end of 6:30 that had, categorical, outcomes, continuous, blah, 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 blah. You might just want to annotate that, right, with some of these keywords. But anyway, All right, Jody, since you brought up oh, go ahead, Chris. Sorry.
No, nothing. I was going to say, I found that in just trying to read 19, I had to go back and just rewrite the definition for certain things: degrees of freedom, null hypothesis, key value. So I think we're kind of sharing stuff along that way, or will at least.
Good, good. So Jody, since you asked for it, did I give it to you?
Yes, thank you.
Good deal, good deal. All right, so remember how I told you the object of our analysis is to reject the null hypothesis, right? That this didn't happen by chance. There's a less than 5% chance or less than 1% chance, right? If the P is less than 0.01, that's even stronger, right? So yay, the data worked out and we can reject the null hypothesis. But what does that actually mean?
That's what I was literally going to say. Is the null hypothesis in general like default that, oh, that was random? So that something is generally random. That's what we're always trying to prove, that it wasn't random. But I mean, can we be more specific and say, I think that X will happen to Y if Z happens or occurs? And then that's where we get into the testing.
Yeah, so kind of. When we say we reject the null hypothesis, we're saying that the outcome of this test has a very low probability of happening at random, right? That's what we're saying. However, the term effect size is one that we talked about, or we talked around it a little bit in 630. But it's I like to use my friend from Massachusetts. She likes to say, well, so what, right? So what? I'm like, hey, it's a beautiful day. She's like, so what? She's got a very thick Boston accent. What is it to you? You know? So what does it mean is what we mean by effect size. I can say that there is a statistically significant difference between Agnes Scott students in terms of their, ACT score and their high school GPA, right? I can say that. Like ACTs that are higher, predict higher GPAs. But how much higher, right? Or how much variation is explained by having certain predictors like high school GPA predict, college GPA. How much variance is that, right? This is taking it one step further. Yes, we know that there's differences in X, Y, and Z, right? But to Chris's point, what does that actually mean if we're trying to predict B or beta or C or, whatever letter you want to say? What does that actually mean? So an effect size measures the size and or the strength of the effect of a relationship of one variable or set of variables on an outcome. Okay? This is different than a p-value. The p-value just simply says, hey, are there differences? And if so, like, what's the probability that it happened at random? Effect size lets you know if you've got a strong relationship between these certain predictors and an outcome, or the differences between the groups, right? So two that I want you to know, and that we'll be running, actually three. We're going to get to the third one later, but these are two. We didn't do it on the t-test because we had other things happening in that class. I might go back and add it. But Cohen's D is the measure of effect size for a t-test. And similar to the R value, right? The R value, it has different levels based on different, classifications. So for Cohen's D, 2.2 and below is small effect. 0.5 to 0.3 or 301, whatever it is a medium effect, and 0.8 represents a large effect, right? So what that means is if we take two groups, right? Let's just take students in my first section of EAM 630 and students in my second section of EAM 630, and I bet y'all can't wait for this, huh? If we compare those two groups by how much they picked on me in class, right, by the number of jokes that were told each class, then my first section, right, would be significantly higher, or there would be a difference between the two groups, because my second section was very polite. They were kind, they were courteous. I'm probably going to go to their weddings, right? I think I'm already going to be a godparent for one of them. So they love me. I'm joking with y'all. I'm just making this up. But let's just say these two groups are different, right? By the number of jokes that are told in class. How different? How different? If, let's just say Cohen's D came back at 0.01 or 0.05, that's a very small effect size. Maybe the difference, maybe because we had so many students in both classes, it just happens to be a statistically different relationship, right? Statistical difference is actually significant. But when it comes down to it, if it's a really low effect size, it may mean, essentially that EAM 630 last spring told like 5 more jokes in the whole semester than the other one, right? There is a difference, but it's very small, right? Same thing with linear regression, multiple linear regression, right? When we predict variables, if we said that, the effect here, we're able to explain only 5% of the variance, 5% of the variance in these data, right? And that for this outcome are explained by the predictors. Well, that just means that, yes, you've got 10, like maybe 1,000 students in your data set. And so naturally, there's going to be differences between, GPA and high school and GPA in college, but it's a very small proportion of difference that's actually explained by those variables. Okay. Does that make sense, y'all?
Can I ask though, while you're on that,
Of course.
Well, I think you just said it. I just want to make sure that's what you were just saying about the size of the class or the sample size. I remember certain things are allowable. I mean, like you wouldn't use certain tests if there were a small group and I say that because I feel like one of the little, never mind, I'm not going to get into that, but No, you're good. You're good. Yeah, non-parametric tests, if you don't meet those assumptions, right, that's what you would go with for smaller samples. But even if you meet the assumptions for the parametric test, you may not, you may actually have so many people that the differences are just outright, right? And so, if you go from maybe 200 students to 500 students, more than likely you're going to be able to determine significant differences, right? Just because of the sample size. That's one of the limitations that field does talk about. So that is something to think about as you notice, like, oh my God, everything's statistically significant in my data set. This is great. Well, if you have 20,000 records, remember that data set when we looked at art? Yeah, how many records were in that? There were a lot.
Like 60. Yeah, 60,000. Remember the donations for political parties? Like 500,000, right? Everything was significant. So anyway, all that to say, we're going to talk about Kramer's V and how it relates to chi-square as a measure of effect size a little bit later on. But I wanted to really kind of go back and talk about this. And by the way, this review is testable. Okay, we can have this on the exam. Oh, Jody, I just heard your eyes roll.
No, I knew. I'm not surprised. I knew. Anything you say is subject to being on the exam.
Cool. Well, no, I don't mean anything negative. What I mean is
no,
you need to know this, right? Like this is stuff that I kind of wish we could have dug into more, but I don't think, and correct me if I'm wrong, we didn't have any downtime in our class, very rarely, right? So, okay. Don't tell the others that they missed out on this fantastic review, right? Okay.
I do have a question though. How many people were in the second section? I'm just curious.
7 or 6. I think we had someone drop. Someone dropped out.
Okay.
And I think we ended up with like 6, right?
Yeah, I just remember on our presentations we had 2 groups of 2 and 1 group of 3.
That's it. Yep, 7. Yep. And actually, no. We had one group of 1.
That's
Juliana presented by herself. Ken and Mamta were together. You and 2 others. So it was 3, 2, and 1. Yeah, so 6. All right, we can do math. How about that? What? Okay, now let's move on over into the bond further correction. By the way, notice the blue bars. Bond further correction. Okay, you heard me say a little bit ago that if the p-value is less than 0.05, that signifies that there is a statistically significant difference between whatever we're looking at, right? And then I said the word that you hate, which is maybe. Maybe, right? So let's talk about error. Let's just talk about statistical error. There's 2 types. Type 1, we believe there is an effect, but there isn't. So it comes back as p is less than 0.05, but when you really look at the whatever population you're looking at, you find out, you know what? It was just that less than 5% chance it got us, right? That sample was just the people that would show the effect, but in reality, there's not, right? We talked about this a little bit at the onset of our class last time, so I just want to kind of go over it. Excuse me. The second type of error is type 2. This is when we don't believe there's an effect, but there is, okay? So our data comes back as p is greater than 0.05, and we're like, oh, all right, whatever. But in fact, again, based on the sample, based on parameters around the test, based on the environment we're in, maybe there is some difference. So the one thing I want you to take away in terms of the Bonferroni correction is basically we need to be able to account for type 1 error, right? And so think about it like this. You've got a data set that I'm going to ask you to run a couple of different chi-square analyses on, right? That's going to be part of your homework. Well, essentially what happens when you run multiple analyses on one type of data or one data set, the likelihood of you coming up with a significant result when there isn't one inflates. It gets bigger because we're not accounting for the fact that we're basically reanalyzing the same data, maybe in different ways, okay? So the first thing to do is to take the number of times that you test your data, right? The number of tests that you run, and take 1 minus 0.95, raise it to the number of tests, okay? So if you do 3 analyses on that data set, it would be 0.95 raised to the 3rd, and then subtract it from 1. Or for this example, 5, right? So 0.95 to the 5th minus 1 is 0.222 or 0.226, which means let's say this all like in a much more coherent way. When we talk about combating type 1 error, if we're only doing 1 test on a data set, 1 minus 0.95 to the 1 is
0.05.
0.05. That's our significant value, right? Right. That's the likelihood that we would find type 1 error, right? Or likelihood that we would have a statistically significant difference. That's perfect, right? That's exactly what we want to see. However, we ran this data analysis 5 times on the same data set in different ways. Our 5% chance for finding an effect when there isn't went up to 23%, which means
Thanks.
1 in 4, right? Okay, makes sense? So the way we combat this, the way we do this, the way we figure it out is we make an adjustment to the p-value. instead of just being like, all right, well, there's a 23% chance of error here. Let's just go on about our business and publish our scientific research in the most prestigious journal. No. We take the alpha value and we divide it by the number of tests. And for some reason in this equation, N turns into K, okay? So alpha value that we're setting for this analysis is 0.05. We're going to divide it by 5, which means our new P critical value that we need to be less than in order to have a statistically significant result is what?
0.01 you have there, right?
That's all right, 0.01.
And you said
0.01.
K
What if we
is
did 10?
K is
Oh, the number of times you analyze the data. Yeah.
okay.
It changes from N to K.
Just to confuse us.
Not my choice. Yeah, not my choice.
And what does the
Okay. So
CRIT stand for?
Yeah. Critical p-value.
Okay.
Yeah.
Okay.
So our initial p-value would have been 0.05, but because we ran the chi-square 3 times, right? It's
Gotcha.
0.05 divided by 3. Yeah. Makes
Got
sense,
you.
y'all?
So it's critical when we basically divide it, when we are talking about multiple. But what I don't understand is when you said, and we run it in different ways, same data set, but run it in different ways, meaning like all those different tests we learned about, like Whitney versus blah, or like, what do you mean by that?
Conduct a chi-square test with this, conduct a second chi-square test with this, conduct another chi-square test with this. That's 3 tests, same data.
Okay.
Yeah. Then, okay. So this is a correction. This is basically being conservative with our estimates because we don't want to basically slice and dice our data in so many ways that we generate significant results eventually, right? I call it the dissertation in progress, where like you're just trying to find something that's significant. No, you don't want to do that. Okay. All right. Any questions about this? It does have 2.2 bars, in my opinion. I don't know what it has in field.
No, I mean, is it better to say I ran this 4 times and of course then you have to remember to have this critical value, and I guess just to check. I mean, what's the purpose of saying just?
Yeah, good question. So doing the Bonferroni correction changes your critical p-value from 0.05 to whatever, like for here, it would be 0.01. So for each of those analyses, if you got a p-value of 0.035, it would have been significant had you just run it alone. But because you ran 4 other tests, it doesn't meet the criteria to be considered statistically significant because you're running multiple tests on the same data.
Okay.
Kara?
I was just going to say, so if you're going to run a lot of tests and do the Bonferroni correction, you would basically be able to have more confidence in your results.
That's right.
Okay, thanks.
Okay, that's what I was just like, is it better to do that? So if we're reading like some scholarly article, I should feel good if I see the critical P, because that means, oh, you all really ran the data.
You might not see critical P, you might see Bonferroni correction yielded blah, 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 right?
Okay.
Yeah.
Cool.
Yeah, I don't know how often you'll see that P crit designation. Okay, so that's it for this at least initial review. How are you feeling?
That's good. So, well, because I did come up again with that the R And something else, and I think that was what my comment back in our chat was, I know I wrote down to calculate R, z-score divided by square root of the sample size. But like the letters, I get so confused when we run a test and you got all these damn letters and, oh no, it doesn't mean that. This time it means M, that time it means K. And so that's where I'm like, okay, wait a minute. When you say the P value, but it really, because if we ran this kind of test, the P value is Z equals, or, I just want to make sure I have those kind of, I wish I had like a little chart. Maybe I can create that so I can say when I see P, it equals this. Did you create that already?
No, but must see someone else did. Girl, I'm lazy. Statistical value.
But yes, the review was great. Thank you.
Yeah. Do what?
I said the review is good. I mean, I thank you for that.
Okay, good.
But it's just when you start getting all the results from SPSS, you're like, yeah.
Yes, it's like you think you know it, and then you're looking like the cat example that when you ran this, and then I'm like, okay, I don't understand this at all. So
I love this website.
Yeah, so can you shoot us in the chat?
Yeah, this is to
Yeah.
figure how to. It's handy.
Oh, this is what okay, thank you. You're on it, Kara.
I put
Kara,
this
what?
in our, well,
You
in
did.
our Google space, you guys. This is what, this is like 3 days ago.
Yes, I'm saying, yes, you did put that there.
Yeah.
So
Oh,
thank you.
okay.
Kara's like,
I
y'all
guess-
pay attention in the Google chat.
I just hadn't clicked
Come
on
on,
it
y'all.
yet.
Get with the program.
I just mean that's where you can find it. If you forget, that's all.
It's missing some stuff. I would have added a few more, but anyway, try this one.
Yeah, I'm just gonna bookmark it.
No, that's not it. Anyway, okay.
Oh, it's nice too.
I'll be on the lookout. I'll be on the lookout for some more. Don't worry. All right. So, okay. Anything else before we get into chi-square? Okay. Now, has anybody ever watched Monty Python? It's time for something completely different, right? Here. This is, so I wanted to start this semester not really building out from correlation, linear regression, deeper and deeper into the kind of linear modeling, continuous variables. But I didn't feel like I felt like, number one, you need to talk about chi-square and logistic regression, but there's not really a logical place for it because they are categorical outcomes. So I thought I would do these first in order to get everybody at least on the same page, and to kind of help you like work yourself into this class a little bit more. Chi-square is pretty common, and you actually probably do it way more often than you think. You don't do necessarily chi-square, but you do analyze associations between groups, okay? And so the differences with this kind of analysis is that before last semester, when we did t-tests, when we did linear regression, when we did parametric tests, or I'm sorry, non-parametric testing, we were always looking at some sort of continuous outcome, right? The outcome for the t-test was, blonde-haired people or red-haired people, who has a higher IQ, right? IQ is continuous. It's a continuous variable. When we were looking at, Kara, remind me about your project presentation.
Oh, I looked at, what did I look at? A number of texts sent per day by kids in grades 9 through 12.
And what happened? What was the outcome of that analysis? Like, what were you trying to look at, prove or predict?
I wanted to see if it increased or decreased over time.
Right, there you go. So continuous. Yeah. Again, right? Like number of texts for the outcome variable. that is a lot of what we're going to be doing for the rest of the class, is continually analyzing continuous outcome variables. That's not always the outcome, though. That's not always the outcome. I like peanut butter and jelly sandwiches, right? Proof right there. Proof is in the package. I like creamy peanut butter only. Shut up. I'm sorry, I'm boring, y'all. I like creamy peanut butter and I like grape jelly. I'm pretty sure I could, I don't know, do y'all like peanut butter and jelly?
Love it, but it's got to be crunchy, and I like blackberry jelly.
Yes and yes.
Okay.
Yes and yes.
Okay. Okay. So if you had a Montez, what about you? Do you like peanut butter?
Sorry, I didn't hear.
Do you like peanut butter?
I do, but I like strawberry jam more.
That's okay. That's okay. We can work with that. All right. So here's the deal. Let's just say students and faculty. Those are our two groups that are predictors, right? Kind of, sort of. So students prefer crunchy peanut butter overwhelmingly, and faculty prefer creamy peanut butter overwhelmingly, right? What's the outcome? What is the outcome? Is it continuous?
Either or.
It's categorical, right? It's crunchy or creamy, right? It's group assignment is what we're talking about here. So people belong to groups on the predictor side, on the equation side, and then people belong to groups on the outcome side as well. So really what we're trying to do is look at the differences between groups and look at whether or not there are associations. Like, what if 75% of the faculty preferred crunchy peanut butter and 50% of the students preferred crunchy peanut butter, right? Then 25% of the faculty would prefer creamy and 50% of the students would prefer creamy. The question is, are those associations different, right? Is there a difference between these two groups in terms of their preferences for peanut butter? So it's kind of like a t-test, because we're looking at differences in groups, but not really, because the outcome is not how many texts a student would send in a given week. It's what group assignment do they prefer or do they belong to? So in layman's terms, or not so layman's terms, the purpose of a chi-square is to compare frequencies that we observe, right? So the observed number of people that says crunchy or creamy, and compare them to what you might expect to get in those same categories, those same outcome categories by chance. So like we talked about before, 75 students said, or 50 students said creamy, 50 students said crunchy, 75 faculty said creamy, 25 faculty said crunchy. That's our observed values, right? That's what we know, right? That's the data that we collected. What the chi-square test does is it compares those observed values to a calculated expected value, okay? And I'm going to walk you through how to do this by hand. We're going to do it by hand, and then we're going to do it in SPSS, okay? All right, so everybody knows everyone's got a preference for pets, right? Go ahead, Jody.
Are we going to have to do it by hand on an exam? And I'm not saying I won't pay attention if you say no. I just want to be mentally prepared for that.
You might.
Okay.
Okay. So here's what we know. We have analyzed, I guess, like 962 people, their preference for their pets, right? And we know what their gender is. And so it appears that both male and female prefer dogs over cats. Can y'all agree with me on that? 231 versus 242 and 207 versus 282, right?
Right. Agreed.
Right. So what we want to do is find out, hey, are these associations different between men and women? Are they different, right? Is there more of a prevalence for men, even though it's higher, right? The sample may be higher for men. We might have more men in the sample than we do women. I don't know, vice versa. So the first thing we have to do is recognize, remember I told you before, we're going to compare observed values to what calculations will give us are called expected values. So these are our observed values. Remember that and put it in the back of your head for a minute. The first thing we need to do by hand is multiply the row total by the column total for each category, okay? So, ready? 473 times 438. 489 times 524. You see how this is 524, this is 438? 231,
Sorry, can you say that, do that
4,
one more time? I'm sorry.
Yeah, no, you're fine, 231 plus 242 is 473, right?
Mm-hmm.
231 plus 207 is 438. We're going to multiply 473 times 438 and then divide it by 962. Okay? Then we're going to multiply 489 times 524 and divide it by 962 to get this expected value. So this is how we calculate expected values. 473 times 438 divided by 962 gives us the expected values for females that prefer cats. 489, 524 divided by 962 is the expected value for males that prefer dogs. 489 times 438 divided by 962 is expected male cat lovers. And then 473 times 524 divided by 962 is expected female dog lovers. Okay? A little bit of math. So then that gives us our expected values. Okay? And this is what they are, right? So just trust me on this. I can pull it up real quick. Give me a sec. Here we go. There we are. All right. So 473, 438, 524, 962, right? 489. 473 times 438 divided by 962, right? 489 times 438 divided by 962. So on and so forth. Okay. So these are the expected values. Those are the observed. Okay. Next, what you have to do is basically subtract the expected values from the observed and then square the result and then divide by the expected value. So subtract the expected, B, or whatever it is. Sorry, I've got to go all the way over here now. There it is. The expected value is G2. I'm using the column and row references. So G2 subtracted from B2, right, the observed, and then we square that result, and then we divide all of that, again, by the expected value. And we do it for each cell in your chi-square table. Okay? So each cell in the chi-square table. Does that make sense, y'all? Once you've done that for each cell in the chi-square table, all you have to do is sum each of those 4 values. Just sum them all together, add them all up, and it's 4.0, Don't know what that 9's doing. 4.10. That is our chi-square value. 4.10. So it is a little bit of a process, but it's really not hard math, right? Jody's looking at me like I'm crazy.
Oh, wait a minute.
It's really not hard math.
Go back to the right. You said the sum of what now?
Yeah, sum of each of those subtracted and squared values. Just
I got you.
sum them all together, and it's 4.10 down here at the bottom. I just put it over there as well.
I'm sorry. And can you go back to the expected where it's the 215, which is not the number in the little box, and walk me through that again? I'm sorry.
Right here?
I'm sorry. Yes, sir.
No, yeah, you're good. So we have all of our frequencies, right? For all of our people who loves cats, who loves dogs. We've done the sums across, right? And the sums, and the sums below. And now what we have to do is multiply the two corners. So for this first one, cat female, my bad. Cat female, you take the row, multiply it times the column, and then you divide it by the total. For the dog for female, again, row, column, divide by the total. For male, row, column, for cat, divide by the total. And then for dog, again, row, column, total, multiply it times the column total, and then divide by the total. That gives us these bigger numbers. And then you come over here and you subtract the expected from the observed. And when I say observed, that's just the frequency distribution, right, for the table. So take B2 minus G2, subtract the expected from the observed, square it, and then divide by the expected again. Or do that for each one. And then you get your chi-square by summing them all together. Don't worry, I'm going to give you this Excel file. Okay. So what do we know? Our chi-square is what? 4.10, right? Boom. There it is, right there.
Which is less.
Well, what does that mean? Go ahead.
Less than 5.
Go ahead, Chris.
I just remember that if it's
Do
less
what?
than 5, then that means we need to use something else we do, and that's where the Kramer's V or whatever comes in, I think. But I know that 5 means, wait a minute. God, I wrote that down. Where are my notes failing me right now? But I know that, I don't know how to take on. I don't know how to take, I don't know how to put 4.10 into a sentence.
Don't worry, you will. You will.
Oh, here, now they're on the back of my card. Now I found it. Expected frequencies in a 2x2 contingency, which is what that was. No expected value below 5. And that's a part, I guess, the expected. So we were actually, the expected values was like 250. So they are above, they meet the assumption. It's not, I was thinking the chi-square is below 5, but that's not what we're saying. It's the amount in the actual square. Okay, carry on. That's all I'm gonna say. That's all I remember for now.
Okay, anybody else want to chime in? So we have this chi-square value. What does it mean?
Well, the chi-square is saying that there is a connection, or connection is not the word. There is a, because I remember, okay, so I have here that the chi-square assumptions are independence and expected frequencies. I mean, those are what we're looking at, and that they are independent variables. I mean, I don't know. I'm creeping in there. Somebody save me.
This isn't the residuals part, is it? The absolute value of the residuals? Okay.
Oh. Okay. Okay, I got another one. Because we also mentioned right in that part of the chapter, likelihood. So there is a likelihood that being a man or a woman has an effect on if you like cats or dogs more.
I would call this an association when you talk about chi-square. You're saying that there's a relationship or an association between group preferences.
Okay.
But yeah, don't worry about, you're getting ahead of yourself because you're trying to explain the outcome without knowing if you don't even know what the outcome is yet.
Yeah.
We've got a chi-square value, but we don't know if it's even statistically significant differences between these groups, right?
Uh-huh. No, we don't.
No, we don't. Well, let's open this up real quick. This is a chi-square distribution table. And the way you read it is first you figure out the number of degrees of freedom in your test. And then you come over here to find your alpha value that you want to use. And what's our alpha value? Everybody should know this.
0.05?
0.05, right? So that's easy, right? 0.05, boom, there it is. Do we know our degrees of freedom?
When it won?
Well, good guess.
No,
But,
that wasn't
yeah.
a guess. I remember I have a whole card and I read a whole stinking thing about that. I went back to the soccer. I knew
you're
this
good.
one.
I'm just messing with you. So here's how we have to figure out degrees of freedom, y'all. This is the next step. You take the number of rows minus 1 and multiply it by the number of columns minus 1. How many rows do we have?
2.
How many columns do we have?
2.
2 minus 1 is?
1 times 1.
2 minus 1 is? Times 1 is?
1.
1 degree of freedom
Mm-hmm.
at the 0.05 level.
Mm-hmm.
The chi-square that is at the 0.05 level is 3.84. What's our chi-square value?
Oh, what was it? 4 or something? The number, I can't remember what it was.
4.10.
Okay.
Yeah, 4.10. So if it's greater than 3.84, that means it actually has a p-value of less than 0.05.
Oh God.
Do you see that? It's somewhere between 0.05 and 0.025. But what that means is that there is a statistically significant association between gender and pet preference. So the way you read it is, hey, 3.84, 0.05, 0.0525 is 5.02. It's somewhere in between there. And so this, Chris, this is what I think you were trying to get at. This is how we report the results. A 2x2 chi-square test revealed the proportion of males and females' preference for pets differed by gender, with chi-square with 1 degree of freedom for 962 people equal to 4.10 with a p-value of less than 0.05.
Wow. Okay.
Oops, sorry. Y'all need a minute to let that sink in?
No, I was just, I was thinking back to, I was trying to think of how when you did the columns, the number of columns minus 1 times the number of rows minus 1. I went back to, I mean, that was an easy one mainly because, but I went all the way back to whatever chapter he said, go back to, and talked about the soccer team and the roster, filling everything in. And there's 1 degree of freedom in that example as well because of how he was filling up the roster as each soccer player entered into the room. so that there's one that had no choice. You had to go into that column. So that's kind of how I was rationalizing it. But I would like to see if I saw, 6 by 5. Is it ever even odd, or is always? Can you do that?
No, it's even odd. Yeah.
Okay.
Yeah. Sure.
So 6 minus 1.
But yeah.
6 minus 1 is 5, and 5 minus 1 is 4. 20 degrees of freedom. Okay. And then 20 degrees of freedom on that column would be 314.
A chi-square value of 31 or less.
31. Okay. Yeah. 30. Okay. Because of 0.4. Yeah. Okay. Okay. And then that's would be okay. I don't know what that example would be, but I was just.
This chi-square distribution table is out here in Canvas for you. Okay. Make sure you download it. Yeah, no problem. Okay, so that's what we know, right? Isn't that fantastic? We know something about males and females. No, I'm joking. I know nothing about anyone. But what about effect size? It's a statistically significant difference in how these two genders are associated with pets. But remember, I told you before, there's more than just statistically significant differences here. We need to know what kind of effect, if it's a medium, small, or large effect, right? Because a p-value less than 0.05 doesn't necessarily mean that the variables are strongly associated with each other, right? Even a weak association can result in a small or low p-value, right? P-values just, they're different, right? Statistically, they're different. It doesn't mean that they all like to play with each other in the, I don't know, pet adoption center or whatever. So let's talk about effect size. The effect size measurement for chi-square is called Kramer's V. And so this ranges, it doesn't have the 3 pretty little, segments like low, medium, high. It just ranges from 0 to 1. 0 means there's no real association between the variables, and 1 means that there's a perfect association. And I'm going to save you all some time. You can't calculate this really in Excel very easily, okay? So before we go into SPSS, remember I gave you this data, right? And we calculated these beautiful, calculations on the sides of it, right? What if I gave you this data? What if I gave you this data? Would you hate me?
Oh gosh, I just now saw how many numbers. I'm looking at numbers on the left.
That's 962. This is the data.
Oh yeah, crap.
What if I gave you? What if I gave you this and not the summary table itself? What would you do?
Well, that's where SPSS.
Besides say, oh crap. No, what if I told you to do it in Excel? To get to Jody's point, we'll just be on the exam.
I think I would change that male and female to 1 and 0, and cat and dog to 1 and 0, and calculate from there.
Okay. Yeah, well, you don't have to do that. You can actually just filter. If you go to filter, you could change them to 1 and 0, right? But you could filter and do cat female, right? That is 231, right, Manta? Right? So you could filter and figure it out there. Or if you want, which is my preference, go to insert and then hit pivot table. And make sure the little ants are marching around the columns A and B, and hit OK. Bring gender into the rows. Remember how I told you about the rows and the columns? Gender in rows, pets in the columns. The outcome that we're trying to measure the association for is always in the columns, okay? The grouping variables are always in the rows. So we've got males, females, and cats and dogs. We don't have anything in there. All you have to do is bring either one of these variables into the sum of values section, and it'll do a count for you. We just recreated that table. 2 seconds. Make sense, y'all?
Yeah.
Okay. Okay. And now, you know, if you were doing this in Excel, all you'd have to do is literally just, just take it, copy it, paste it, and then do your other calculations on it. Don't do calculations here because it's part of the pivot table. It's really weird if you try to like select stuff. It turns into this weird like get pivot data situation. So,
Okay, thank you.
All right,
You may have made me hate
right.
pivot tables that much more, less, just from that statement about grouping is always in rows. Outcome is, I'm always like, which ones I stick them in? I waste time goofing around with it. So thank you.
Yeah, no problem. Columns are the outcome. All right, so here we are in SPSS. And this is the data, like I told you. Same data file, right? I just brought it into SPSS. The way we do chi-square in SPSS is under the Analyze menu.
Mm-hmm.
And then we go to descriptive statistics. It's actually a descriptive statistic because remember, we're looking at frequency distribution. We're just looking at the way that frequencies fall within categories. So it's actually housed under descriptive statistics, under cross tabulations, because essentially that's what it is. It's a cross tab. So remember, I must have already done it before class, but yeah, gender is rows, pets are in the columns, right? Under statistics, choose chi-square and Kramer's V and hit continue. And what did y'all learn last year for me?
You always paste.
What do you do next? Paste it, right? Paste it. Just save it because it's easier to do like that. So now we know we're doing a table gender by pet. Statistics are chi-square and phi. Cell counts. Oh, I didn't see. I caught myself because I looked at it and like, oh, I forgot to do something. Under descriptives, cross tabs. You can also click on cells and do row and column percentages just to see what the distributions are. I like to look at them like that, but you don't have to if you don't want to. So now there it is. Row, column, yep. And now hit play. And I'm not connected. Dang it. Sorry, y'all. There it goes. Okay. I'm not on my VPN right now. So I'm on my personal SPSS. But here we go. Look at that. Pearson chi-square 4.10. Can y'all see it?
Mm-hmm.
I know it's small. Apologies, Kara. I just saw you did the lean in. But yeah, 4.10, right? Hey, look at the significance. It's less than 0.05, right? Right? And it's actually between 0.05 and 0.025, which is even better. It shows us that that table is right. If it was like 0.001, I'd be like, let me think about this because my chi-square table said it should be between 0.05 and 0.025. All right, so there we go. That's the difference. But we're doing this not only do the chi-square, but we're also looking for the Kramer's V. Kramer's V. Look at that value. What does that mean?
It's not zero, so there is an association.
Not zero. There is, but what would you say? Go ahead, Kara. Sorry.
I was just going to say it's slightly over 50% of a nice association. It's like closer to a good association than
I saw
not.
0.067.
Oh, you're right. Well, that's real tiny then.
Really tiny. But we have a lot of people in our sample, right?
Yeah.
So differences get, noticeable more the more people you have. But when it comes down to it, the Kramer's V value of 0.065 means we have a very low strength of the association.
What's phi?
So now all we have to do is add that V to the end. Okay.
Great. Oh, that's for the Kramer's V. I'm like, and there's another letter.
That's what I was looking for on the website. I didn't see it, so that's why I was immediately looking for Kramer's V. I was like, well, I don't see it. We'll find one. But anyway, all right, y'all. So have we done what we said we were going to do?
Yeah, I have one question though. So on page 852, where they walk through exactly kind of what you did, they had a whole bunch more screens in here, like exact test. I mean, we're going off of what you're showing us.
Fisher's exact test. Yeah. No, don't worry about that with us. Okay.
Okay.
Not tonight.
I'll
I'll try to. Yeah.
All right, that's fine. I was just comparing the
Yeah.
was there.
No, you're good. Are you sure it's 852?
Not the page number.
Oh yeah, page number.
What's the page?
Oh yeah, no, on page 852. Wow, it's weird that it's 752 when I made that statement. But anyway.
Because I'm in my version of the textbook. Go ahead. Sorry, whoever said something.
I don't know what version I have, but
Okay, now I'm really confused because I'm on like in the 600s.
I'm in the 600, y'all. Yeah, I'm at 620 something. 620.
This has the advanced novel.
Oh, I have the
version.
5th edition.
Okay.
This one.
I gotcha.
Oh.
Well,
So
yeah.
do I. What are you
Yeah.
talking about, lady? I'm on mine's like 625.
620. Chapter 19?
Yeah.
Oh, well, you didn't probably have to listen to all the crazy. Maybe it has less Andy in there. Less of his personality.
No, it's pretty Andy intensive with his dancing cat video.
Yeah, 600 is like chapter 13 for me.
Yeah, I'm on the online version too. So, let me do something real quick. All right, so what we're going to do next, y'all, is I'm going to put you into a room, like a breakout room, give you a chance to talk to each other about it and work through a different file. It should be coming your way here in just a second.
One thing.
Let me know if you,
When are we assuming we're going to have to do the part where we explain this to some poor person who lives in our household? Or well, first let me ask, are we going to have to do that?
Yeah.
Okay, well, can you go back to that slide? And okay, I just want to make sure so I can warn my husband. And can you go back to that slide and walk me through it in SPS for Dummies language?
Oh yeah, sure.
Stop. Don't do this.
This is how it always is, y'all.
You started.
Ready?
Thank you.
Yeah, I know. So here's the deal. So we did a little community survey for the pet shelter, just finding out people's preference for pets, and come to find out that males, even though there is a difference between males and females in terms of their preference for pets. A higher proportion, and this is again going back to the frequency distribution piece, you can say a higher proportion prefer dogs on both sexes, but there is a difference between males and females in terms of how much of a proportion prefers cats over dogs or dogs over cats. But when we looked at it a little deeper, there was very little impact of that analysis. So even though there is a difference due to the large number of people in the study, it's really not that big of a difference between the sexes. You all agree with what I said?
Yeah.
Okay,
That's why it's a famous, that's why it's a famous question in like, are you dog or cat? You know, sweet or salty? It's probably the very same thing. Popular because it could swing either way.
Right. So now you are expected to do chi-square analysis on your own. Good luck. I'm going to put you in a breakout group. I'm going to give you 20 minutes. Okay. 10 minutes of that, you can do whatever you want. Take a break. Okay. Sound good?
No. I'm sorry. I was still stuck on your instructions over there. Sorry. Go back to the break and the data set. The data set's in the
in your email.
And email. Okay, I got to get there. And you're putting us in the breakout room first, then go on break, or what now? Sorry.
You take your break whenever you're ready. Y'all can talk amongst yourselves and I'll take a break at the same time, or if you got to pee, go pee, right? I'm not going to stop you from that. I just know that I've been talking for an hour and a half at this point, and I try not to do that too often. So take your break whenever you're ready. We're going to all come back in 20 minutes. I'll jump in maybe once or twice just to see how y'all are doing, but use this to talk to each other and work through this, okay?
Okay.
Ready? Don't be scared, Chris.
I'm not. I'm just
Sarah,
not. I am not taking in the information. I'm like, what? I'm gonna get in the break room, and whoever I'm with can tell me if I can go on break or not.
Wait, we're all together, right?
You're all in there, all together. Yes.
Oh,
Sarah?
see.
What is NR in this data? Do we not know? Okay, I can tell by your face. Great, thanks. That answers my question.
No, good question. Good question. I got you.
Since
Let's
it
go
says
over it real quick.
white and known minorities under race, do we only then count WH and MIN and anything else we're ignoring?
Yes.
Okay.
So white is WH, MIN is known minorities, UN is unknown, TW is actually TW is in a minority because it's 2 or more. NR is international.
Okay.
And we don't know their race. So,
okay.
So that should be it. Yeah, I think. Basically, yes, white and minority. Thank you for paying attention to the instructions.
Mm-hmm.
That was what I was caught
Ready?
on. I was like, what are we talking about? The data set.
Everybody ready?
Yep.
Yes.
I'll see y'all in a couple of minutes. I'll check on you.
Okay.
Jody, you there? Hey, Jody. Cool. Hey,
Hey,
hey, I gave it, I forgot to make it to where multiple people can share simultaneously. So hopefully you can share now.
okay,
Sorry. How's it going?
okay.
Okay. Don't forget to take a break.
Will do.
Okay.
We'll reconvene in like 15 minutes, I think.
Oh, I guess I do need to take a break then. Yeah, see, I wish we'd have taken our break, because once you give us the numbers, then we're all trying to get it. And then there's not, because we're not really competing, but we don't want to be so far behind where we're asking if we could have all
No.
worked together through it.
This is the Hunger Games version of data analysis. You got to compete.
No, I mean, I'm not saying that. I'm
Okay.
just, oh shit. Oh, no and yes. Okay, that's the part I'm like, I don't know if those are no's or what. Okay, sorry. I didn't label that. I didn't grab that over.
All right. Anybody have any questions?
Not yet.
All right. Yeah, a little bit.
I will say it feels good to, it
Being
makes
class.
it does. And then I also, I just like knowing about the stuff. I mean, I haven't had necessarily to encounter anybody that's using these calculations at work, but I love when I read an article and I'm like, I know what that means, or I've seen that, or at least I know where to go look to get the answer. I mean, it's better than just like, I don't know what the heck that any of that stuff is saying. So anyway, I just thought I would share that.
Cool. Yeah. No, I appreciate it. Good to hear.
And how far out on average should we go with our decimals, past the decimal points? Like 3?
For chi-square, 2, fine.
Okay.
Yeah. That's okay.
Oh, sorry, I got all my clicks are going. Sorry.
No, you're good. I'm clicking around here too, y'all. Did you get 36.302, y'all? Yes? Good. All right. Who wants to tell me what's big? All right. Who wants to lead?
Okay.
Oh, you didn't ask us to do the V.
Did not.
Oh, I was
That's
like
okay.
going so fast to get to SPSS.
No. Add it. We'll call it extra credit for 0 points.
Well, I didn't get there, so it's fine.
Oh, okay.
Chris, did you want to go? Go ahead.
Who wants?
No, I mean, I'll try it though. So I'm trying to remember. Okay, so chi-square is, and I only did 2 decimals, like you just said, so 36.3.
Wait. No. Chris, look at my screen.
And x chi-square. I am looking at your screen. Where?
So fill in the blank. What are the blanks?
Yeah, that's what I was just reading the blanks. So I was going chi-square, which is before the first blank.
No.
Oh, there's first generation. That's the
Good
first
job,
blank.
Maranta. No, she got it right. She said 2 by 2 right here.
Oh, okay. I didn't even see that. So, all right.
Yeah. No, it's all right. So remember this, right?
Mm-hmm.
Yeah. There you go. Keep going.
Okay, so I don't remember it completely, but okay, a 2 by 2 square, a chi-square test revealed the proportion of people who reported, or students who reported being first generation. I don't know, first generation. I don't know.
It
I don't know.
differed by race.
Okay. Yeah, and see, I had a little screenshot there, but I'm just not there. I wanted to write all that out yet. I hadn't gone to that. Okay, differed by race. Chi-square is 36.30.
Wait.
No.
What's this? What's this right here? The degrees of freedom.
Oh,
1.
yeah. See, I need a little label up underneath there, like the first time. This is literally is like fill in the mystery blank, and I don't even remember what the hell they are yet. But I mean, I know the numbers. If you said what's the degree of freedom, this 1, okay, and I remember N. That's easy. Is 1178, which is equal to I need to open my little cheat sheet. And then
Jody and Chris did not get to do this with me very much when they took it with me. This is a Cara Manta section. Y'all, this is how we get y'all to practice in class before you try to do it on homework.
Okay. So which is equal to 36.3, and P is less than, I think on the chart, hold on, let me open the chart back up, but it was 0.05 because it was the first column and a 384. So
yep.
Is that right?
First row.
Ooh,
first row is degrees of freedom. All right.
Right.
Sarah, what do you want to add?
Well, I have a question about the p-value. Since our chi-square value is so crazy high off the charts of the chart, can we say p is less than 0.01, or in my imagination 0.001 if the chart extended out?
What is your p-value?
36.30.
No, that's your chi-square value.
Oh.
Well, that's what I think. That's what we were.
I mean, don't we use the chi-squared in that chart to figure out the p-value?
Right, but you're saying 36 was the p-value. In fact, chi-square is above a 6.63, right?
Right.
So that would make it less than a 0.01.
Okay. And so, yeah. But then my brain goes, well, 36 is hella higher than 6.6. So can I did somebody make this chart to 0.001 anywhere?
I'm sure it exists somewhere, but don't worry about that.
We just don't. Okay, got it.
Okay, so I said 05 because we went, but I can still say 05 though, right?
Mm-hmm.
Okay, so it's just more accurate if you say less than 0.01.
No, still the same. But yeah, you're good.
How good and confusing that is,
all
but
right.
Okay.
Chris.
Don't say anything.
Somebody else.
Oh, okay.
Explain it to your friends and family.
Oh God.
and not Kara's cat, apparently. Forget she's there. Yeah.
Qualified, y'all. So y'all got the others.
she's like headbanging. Yeah, sorry. I'm distracted by the pets. This is perfect for the pet example, right? All right. So who wants to explain this to their family or friends? What was the purpose of the analysis? By the way, y'all, can I tell you, time out, one sec. This is real data for one of my institutions. This isn't made up pets and people. This is actual non-minority, minority students at one of our schools.
Let me ask this question. This
No,
is not
Chris.
no. This has nothing.
No, not until
First generation
not until
what?
someone can explain. No.
I'll have a crack at it.
All right.
If I was going to tell my daughter about this, I would say there was a significant difference in students being first generation when you look at the numbers based on being race or known minority. There's just a significant difference of first generation students between those two groups of people.
Yeah. And you could also add to that the percentage of students in each of those categories, right? Each of those 4 boxes or whatever you want to call it, and say,
sure.
you know, white students are less likely to be reported as first generation versus known minorities, that sort of thing. Okay. So Chris, first generation status is a student who neither parent has earned a college degree or gone to college. In some definitions, I'm first generation because neither of my parents earned a bachelor's degree. And that's a weird definition to me because I think community colleges are colleges too, right? But yeah, that's what we're talking about here. Like being a first person in your immediate family, and even, you know, grandparents and all that stuff to actually go to college.
Okay. Because for a second, I mean, immediately when I hear first generation, and I wasn't thinking about college, I was thinking about born in US. Like, were you that? And I was like, what? That's the part but okay, I'm there. I'm back up to speed.
You're good. Okay, so now I want someone else to tell me how you did it. Start with the software, please.
So I used Excel. And first of all, I filtered the data, and then I only selected the race WH and MIN, that is white and minority. And first gen, I only selected N and Y, and the U was unknown, so just selected that, and then selected that data, and then inserted a pivot table and put race in the rows and first gen in the columns. And then I dragged first gen to value and it counted the numbers for the first part.
Okay. And then
I copied that and pasted to another sheet, and that is my observed value. And then for expected value, I just took the grand total, like the row total multiplied by column total, divided by the grand total.
Yep.
And and then for chi-square, I subtracted expected value from observed value, then squared that value and divided by the expected value. And then,
Perfect. And then
whatever the value came, I added all four, and then it was 36.30235995.
Manta, you're going to teach everybody else how to do the next section because you just walked through that perfectly. Perfectly. Good job. All right. And the next person, someone else that hasn't talked yet.
I'm sorry. I'm still trying to download the file. I have the world's oldest computer. I'm replacing it.
What?
I know. I'm sorry.
What?
I'm sorry.
What? You don't have the file? Oh my God. Oh my God.
I'm sorry. It'll be remedied this weekend. Well,
do not apologize. I was just going to ask you, Jody. Did anybody in the group try to do this in SPSS?
We didn't make it that far.
Okay. So Excel is actually easier and quicker, it sounds like.
We didn't even have our break. How would we go to SPSS?
Well, let me show you how to do it very quickly in SPSS. Y'all ready?
Yep.
Okay.
Recording. Okay, you're recording. Good. Okay, good.
Yeah, well, we've been recording the whole time. So here we go. All right. First thing you do is, you open your data, right? All the data right here, and go to data, and then select cases. Select cases, because remember, we don't want NR, we don't want UN, we don't want U for the first generation variable, right? So this is a little complicated, so I'm going to put it in the chat so you have it, okay? This is why I was in my head, I was like, ooh, I wonder if they're going to try and do it at SPSS because they've got to know how to do this. Otherwise, you're going to be spinning your wheels trying to isolate just these data in SPSS. So Manta, to your point, you could only save a different Excel file or a different tab with just the white minority Ys and Ns, right? And you could save that and put it in SPSS. Or you could go into SPSS and do data select cases, and then say if a condition is satisfied, and basically write out four conditions. If race is white and first generation is Y, close parentheses, right? Or race is white and first generation is no, right? Close parentheses. Or race is minority and first generation is Y, close parentheses. Or race is minority and first generation is no. So basically you tell SPSS like all the possible combinations, permutations of the variables that you want, and then you hit continue and OK, and don't say that. Here's an unknown N. It's marked out, right? And scroll a long way, but yep, there you go. You'll see another unknown race and unknown race N. There's a group of them coming up, I promise. But basically, it works. You merely have to write one group, race of white and first generation, or race of white and non-first generation, right? Here's all the non-resident aliens, the international students that have, yeses for first generation. It doesn't matter, right? We don't want international students in here. Make sense? Okay, so now that that's done, that takes the longest time. Now that that's done, descriptive statistics, cross tabs, race and rows, columns with first gen, statistics, chi-square, phi, Kramer's V, continue OK. or 36.302. Definitely less than 0.001 Tera. Because you see it's like 0.000, right? And then look at our Kramer's V value. Because you did say you didn't ask us to do Kramer's V, right? But if I had, I didn't ask you to do Kramer's V because I didn't know if y'all would be doing it in Excel or SPSS. And I didn't want to freak you out by forcing your hand to do it in SPSS. So Kramer's V is 17.6. That's definitely higher than our last one, but still not very high, right? If all of the white students were not first generation and all of the minority students were first generation, that would be a perfect association, right? Think about like a correlation matrix, right? That would have a 1 of a Kramer's v-value of 1. So it's hard, very, very, very hard to get that. But nonetheless. So, y'all, does that make sense?
Okay, so 1 is a perfect association, 0 is no association, and anything else gives you the kind of the strength in between.
That's
Gotcha.
right.
Okay. I want to write the 1
All right.
part down.
So your first lab assignment for this class, the data is a little squirrely, okay? The data is a little squirrely. Back in 2018, and I'm not lying, this is again, real data, a group of individuals did a census of squirrels in New York City's Central Park. And there are lots of details about the squirrels in Central Park. And so we're going to use that data. It's open source. I want you to run chi-square tests in Excel. I want you to also run yay census data. Right, Manta, exactly. I thought about you whenever I put this in Canvas. I was like, oh, it's the census, but I want you to first do like you did tonight, assess the cleanliness of the data and document any kind of missing information, right? Kind of write it up. Then conduct a chi-square test, looking at whether or not primary fur color is associated with whether or not the squirrels were eating when the census taker documented them, okay? Then bring the file into SPSS. Are y'all laughing yet? Okay. Then document import the file into SPSS, do another chi-square test comparing primary fur color and whether or not their tail is flagging like this, right? That's what a tail flag means. I know way too much about squirrels now because I looked at all this data. Then do a second chi-square test and take the assumed age of the squirrels and whether or not they're indifferent to people, okay? So I just want you to kind of get really familiar with chi-square. A couple of ways to do it. And then of course, there you go, Jody. Describe each of these findings as if you were presenting them at a work or scholastic conference. And I mean it, like, be serious, y'all. And then second, describe each of these findings as if you were sitting around the dinner table with your family. Provide other ideas for analyzing the data, as well as anything to provide additional context. You know, think about it, you know, I mean, it's real, right? It's real data. People put a lot of time and effort into it. So let's enjoy it. The assignment is already open and the point values are defined here like you've seen before. Data management, the chi-square test is the most points, and then output file syntax, data file, make sure you upload those. And then of course your write-ups to audiences, and then any other analysis. So please pardon my attempt at humor, but with this class being so statistically deep, right? Much deeper than the last one we had, I really wanted to find at least one example of data set that would be not as, you know, scary. Unless you're afraid of squirrels. Is anybody afraid of squirrels?
I don't like them. They wreak havoc in my life because of my dogs. But I have a question while we're in SPSS.
Mm-hmm.
I inevitably can never get those stinking files, like to save, and then I can't find the one. So when you hit paste, you get your syntax file, which I wrote deep down so I would remember. SAV is the data set. SPV is the output. And what is the syntax one? What is the extension for that?
SPS.
SPS. Okay. And when I hit save, okay, and you said, and those all end up on the desktop, right?
No, they may not naturally, so make sure they do end up on the desktop. That's the easiest place to find them.
That might be where my stuff is lost.
Have a
Okay.
recommendation on how to name them? Like, just do you do squirrel 1, squirrel 2, squirrel 3? I mean, because I agree with Chris. Like when I look back at my desktop, there's so much stuff on there.
Oh,
Yeah, I usually
Clean up
put
your desktop.
something like that, but I'll say squirrel output, squirrel syntax, squirrel data set is usually what
Okay.
I put. Yeah.
Let me give you all my recommendation.
Uh-huh.
Week 2, name that everything. Week 2, the SPSS file, the output. You know,
Okay.
because here I don't. Okay, so again, not to go back over the syllabus a million times, but I don't know if you noticed this yet, but I'm going to make sure you notice it because I know we're going to do deeper level analyses here. In EAM 630, there were some weeks where you had an assignment and a discussion, right? It didn't happen often, but we had to double up a couple of times. What do you notice here?
There's no overlapping.
No overlap. You're only going to have one thing each week. Give you time, really focus on rewatching, rereading, reviewing, right? Everything, but make sure that you're able to focus on these assignments. Also, you only have 2 exams, not 3.
Hallelujah.
Okay. I didn't hear you. What'd you say?
I said hallelujah.
Sorry, breaking up.
Thank you.
So this is how your grade. This is how your grade breaks down. I forgot to tell you that. Sorry, earlier. So exams are 20%. Your presentations are 20%. Discussion boards on live assignments are 60%. So get your work done. Okay. Great. So who learned how to select data a little bit more efficiently in SPSS tonight?
Yeah.
Kind of cool, right? I mean, think about it. Like how long would that have taken y'all to do?
A long time.
It would have taken a long time, right? It's not one of those things that anyone's ever taught me. So I make sure to teach people what I was never taught for sure. So again, it's just under select. Yeah.
Could we have updated the data set, done in Excel, gone through there, filtered out all the junk we don't want, then uploaded it to SPSS?
It can work. Yeah, that should work.
That would have been, I would have gotten pissed off enough that that would have been my next thing. And then again, then I would have stressed out if you would have said, that's not the original data set. But if I came up with the right numbers, then what would it matter, right?
I care. So anyway, this is your first live assignment. Take your time, work through it. It is due on Tuesday by midnight or 11:59 p.m. right on Tuesday. That's how all the assignments are going to go since this is a Thursday class. When I taught EAM 630 to Jody and Chris, I think we were on a Tuesday night, and you submitted things on Sunday. But at least the Tuesday deadline gives me a couple of days to look over it before we get started. Sound good?
Yep.
What questions do you have for me?
I don't think I had some.
I know you've given us a lot of resources, but I feel like there's been a really big gap between when I took the first class and